Yes, class. Am I audible to all of you?
Yes, teacher.
So in the last class, we had started with phasors and phasor diagrams, and we were able to complete two circuits. One of the circuits included only resistor, and one of the circuits included only an inductor. So Hamza, tell me one thing. Hamza, tell me what is the phase difference between resistor and EMF, current and EMF in case of circuit having only resistor? Phase difference between current and EMF in the circuit having only resistor. Fatima? No idea, Fatima. Atif? Yes, Fatima.
Not by r sine omega t.
No, the phase difference between current and EMF. The phase difference. Yes, Fatima?
Same phase.
Same phase, exactly. There's no phase difference between them. In case of circuit having only resistor. Got it, Hamza? In case of circuit having only resistor, you do not have the phase difference. Both are lying in the same phase. See, this is the circuit containing only resistor. E is equal to E naught sine omega t. I is also I naught sine omega t. There is no addition or deletion of pi by 2 or any angle. Here, value of current is E naught divided by R. And this is how the phase diagram and the graph looks like. See, both are in the same phase. This difference, no, that is coming. This means the amplitude is different. Amplitude can be different. It can have a different value. But in case of the phase, both are starting from zero, from the origin. So it means they are in the same phase. For circuit containing only inductor. Yes, Neha. Is there any phase difference between current and EMF, Sneha? Sarah? Asma? "90 degrees, but which leads what?" Okay, Hamza, right? 90 degrees is the phase difference between them. Kulsum? Which quantity leads the other quantity? Kulsum, EMF what? EMF leads current, EMF lags current. What is this answer? EMF. Okay, Sarah, right. See others who have not revised at all. For the circuits containing only inductor, you have E is equal to E naught sine omega t and I is equal to I naught sine omega t minus pi by 2. Minus pi by 2 means what? Current is lagging behind. Yes, EMF leads current. EMF is ahead of current by pi by 2. Or you can say current lags voltage by 90 degree. And this is how the graphs looks like. Both are not in the same phase right now. Now here we have the resistance value as XL, whose value is omega L, which is directly proportional to the frequency. One last circuit was left. AC circuit containing only a capacitor. This was left. Now here you will be having a capacitor, but now the capacitor, instead of getting connected to a proper battery and key system, this is connected to a coil whose value is E naught sine omega t. The capacitance of the capacitor will be capital C. Now this is what? This is basically the EMF or the potential difference. You can say V is equal to E naught sine omega t. Relation between charge, voltage and capacitance. Hanifa, what's the relation between charge, voltage and capacitance? Give me an equation by which you can connect these three. Hanifa, you're not audible. Are you saying something? Okay, Hiba. Hiba, what's the relation between charge, potential, and capacitance? Yes, Hiba. Charge, potential, and capacitance. How will you connect all these three? Okay, Hanifa. Fine. But what about Hiba? No answer, Hiba. So can anyone answer? What's the relation between current, potential, and capacitance?
Charge equals CV.
Charge is equal to CV. Exactly. Q is equal to CV. This is the formula of it. Charge is equal to CV. From here, you have to know if V is E naught sine omega t, charge will be equal to C E naught sine omega t. So V is this, Q is this. Now, I is given by differentiation of charge with respect to time. I is equal to dq over dt. So it means in place of Q, I can write this whole equation, C epsilon naught sine omega t, this whole equation. Now from here, C epsilon naught is a constant term. Sine omega t will give you omega cos omega t. This is left, this is the equation of current. Now, if you have to write it in terms, if you have to write current in terms of sine, how will you write it? See, this is a constant term. If you compare it with this equation, no, this becomes I naught cos omega t, where I naught has this value. If you want to convert it in terms of sine, you can do one thing. You can add 90 degrees. This becomes sine omega t plus pi by 2. Now, by looking at this, this is the equation of current. And E was what? E was equal to sine omega t. You can easily compare. Both are not in the same phase. This time, additional angle is along with current. This means current is leading this time by 90 degrees. So current leads EMF by 90 degrees. Current leads EMF by pi by 2 or 90 degrees. And current lags behind EMF by 90 degree in case of circuit containing only an inductor. Current leads EMF by pi by 2 in circuits containing only a capacitor. Now, one more thing. This is one of the conclusions that you can derive. But one more thing from here. I naught is this. This will be also I naught from this equation. Now, if you put and write the value of I naught will be equal to omega C E naught. I naught will be equal to omega C E naught, means the EMF. Now, if I transport this in the denominator, this can be written as E naught divided by 1 over omega C. See, if it's E naught divided by 1 by omega C, then this omega C will go up here and your answer will be what? Omega C E naught. So if you write this or if you write this, both of these are same. Got it, class? E naught divided by 1 by omega C. See, omega C will go up only in the numerator. So this becomes omega C E naught. So I can write omega C E naught as E naught divided by 1 by omega C. Both the values are same. It's just that one is in the denominator, the other one is in numerator. Both the values are same. Now from here, this constant term that you're getting, see, if you compare I is equal to V by R, obviously this is the resistant term. This you can write it as XC. XC is what? This is the capacitive reactance. The way we had inductive reactance, here we have capacitive reactance. This is the capacitive reactance. You have capacitive reactance in case of circuit containing only capacitor. The way you had XL, what was the function of a resistor in case of circuits only containing resistor? The resistor offered opposition to the flow of the charges or the motion of the charges. In case of circuit containing only inductor, inductive reactance acted and did the performance or the work of the opposition. Here in case of capacitors, capacitive reactance provides the effective resistance. So it does what? It provides the opposition. It's the opposition offered by the capacitor to the flow of AC through it. To the flow of AC through it. Now let's see a little bit in detail what is this XC. So XC, the way XL was there, try to recall XL. XC is capacitive reactance. This is written as 1 by omega C. Omega is written as 2 pi nu C. C is what? C is the capacitance of the capacitor. All right, class. C is what? C is the capacitance of the capacitor. From here, you can derive one more thing. See, if you plot the graph between XC versus frequency, you get a hyperbola. Reason? Both are inversely proportional to each other. Got it? Both are inversely proportional to each other. And you can modify this formula by whichever manner you want to modify. See, you can write IRMS equal to I naught by root 2. I naught can be written as E naught divided by 1 by omega C root 2. 1 by omega C can be written as XC root 2. E naught divided by root 2 can be written as ERMS divided by XC. So you can use I naught is equal to E naught divided by XC, or you can use IRMS is equal to ERMS divided by XC wherever you have to use it. The way you have been. We'll make a comparison of all those three things that we have studied. Now, one last thing is the graph. These resistance term we have already discussed. But what about the graph? Graph of the AC circuit. When only a capacitor is connected. So let's say EMF is this. This is EMF. Fine, this is EMF. Now what is happening? Current is leading. If current was in the same phase, we would have started from the origin, from here. But right now, current is not behind also. If current was behind, then we would have started from here 90 degree by making an angle of pi by 2. Here current is ahead. So C class, when it was at 0, current had already covered this pi by 2. Now you can complete the graph sinusoidal. This is how you plot the graph for it. Even if you have to show it in terms of phasors. For phasors also, let's say this is EMF, E naught. Now making an angle omega t with the x-axis. Now what about the current? See, here we overtraced, we overlapped it with, for the case of resistance, because both were in the same phase. For the case of inductor, we had drawn the current here, showing that it is lagging behind. Now current is ahead. We'll draw this ahead. This is the current, and this is making an angle of pi by 2. Fine class. So note down all these things. We'll make a comparison. We'll revise all these things. Then we'll proceed towards the numericals. Note it down. Any queries, any doubts, ask me. See class, let's just conclude one thing, then you can proceed with the numericals. For the circuit containing only resistor, what happened? For the circuit containing only resistor, the current and EMF both were in the same phase. Resistance was given by XL firstly. So I naught could be written as what? I naught, not XL, sorry. Here resistance was given by R. So I naught could be written as I naught, you have E naught divided by R. IRMS is equal to ERMS divided by R. For the circuit containing only inductor, current lags by 90 degree. I naught is given by E naught divided by XL. IRMS is given by ERMS divided by XL. XL is equal to omega L, which is equal to 2 pi nu L, and frequency and XL both are directly proportional to each other, so you get a straight line. Last one is C, capacitor. A circuit containing only capacitor. Here EMF lags by 90 degree. You can remember it other way also. Current leads by 90 degree, like that. I naught is equal to E naught divided by XC. IRMS is equal to ERMS divided by XC. XC is equal to 1 by omega C, which is equal to 1 by 2 pi nu C. C is the capacitance, L was the self-inductance. Here you can see XC and frequency both are inversely proportional to each other. That's why we got a graph that was hyperbolic. Now this is the conclusion. At least this much you have to remember. By this information you can draw out the graphs and the phasors as well. Now I'm giving you a question. So copy down this as well as the question that I'm giving. Try that. It's an easy question. Whenever this is given in the question, anything is connected to a source of this much, it means this is the ERMS value. See, for this question, no, pure inductor of 25 millihenry is given. So inductance, self-inductance becomes 25 millihenry. Self-inductance is exactly what you have studied in EMI. EMI, you had self-inductance, mutual inductance, self-induction, mutual induction. No, from there you have self-inductance as 25 into 10 to the power minus 3 Henry. This is ERMS 20 volt. You have to, okay, frequency is also given as 50 hertz, and you have to find out the inductive reactance and the IRMS. Fine. XL is equal to omega L. Omega is equal to 2 pi nu L. So you have, 2 pi, nu from here L from here So XL will be equal to what? 2 into 3.14 into 50 into 25 into 10 to the power minus 3. So this will be equal to 7.85 ohms. And IRMS is equal to what? It's ERMS divided by XL. So ERMS is 220. XL is 7.85. So this will be equal to 28.03 amperes. This is XL. This is the value of IRMS. Note it down. One more question I'll give. That question you all will try by yourselves. At least try this question. See, inductance is given as 1 Henry. It means capital L is given, XL you have. This time frequency is unknown. Other time XL was unknown. This time this frequency is unknown. So this you can at least find out. Second part says XC becomes equal to XL. Then what is the value of C? That this also you have to put it in the formula and check. It means for the second part, XC becomes equal to this amount. At least try the first part first. Send your answers and you get your answers in the chat box. Only Fatima has answered the first part. Others also. See whatever answers you're getting. Fine, sir. So correct answers have been given by Sarah, Atif. Yes, Neha, that's right. See, first part was direct. First part Hamza. Exactly right answer. So I think here you did not need to round it off. No, 314 and 3.14 will get cancelled almost. Just a decimal space. C class. For the first part, XL is equal to omega L, which is equal to 2 pi mu L. This is known, this you know, this you know, this you know. Only frequency is unknown. L is given as 1 Henry. From here, frequency can be written as XL divided by 2 pi L. XL is given as 3142 ohms. 2 into 3.14 into L is 1. So this will be 100, almost 100 by 2, that is, 1000 by 2, that will almost be, this will be 500. You can write value of pi as 3.142, then only directly it will get cut. So 10 to the power minus 3, यहाँ पे it will become 1000 by 2, that is 500 hertz. This is the value of frequency that we get. Yes, Kulsum, right? What's the unit in the second answer, Kulsum? Fatima, did you understand the first part?
Yes, teacher.
All right. Kulsum, tell me the unit regarding the second part that you've answered. See, then the second part says what should be the capacity of a capacitor? Capacity of a capacitor means capacitance. What is capacitance? Value of capacitance. Microfarad. Okay, Kulsum, right answer. That is also correct. Capacitance is unknown. This time it says Xc is also not given directly, but it says Xc's value is exactly what the value is of inductive reactance. Yes, Akhi. Right. So this is equal to what? XL, which is equal to 3142, this much amount of ohms. Fine. Now we can easily predict Xc is equal to what? Xc is equal to 1 divided by omega, which, sorry, not 1 divided by omega, 1 by omega c. So this is equal to 1 by omega c. This is equal to 1 by 2 pi nu c. From here, Xc is known, everything is known, C is unknown. So C will become equal to Xc divided by 2 pi nu. Right? No. But Xc will also come with it. Xc will also come with it. So capacitance will be equal to 1 divided by 2 into 3.14 into frequency is how much? Frequency we've calculated 500. Alright. Xc is 3142. When you solve this, you will get the value exactly like your classmates are getting 0.11 microfarad. This will be the answer. Alright, class, note it down. Then we will begin with a new topic, LCR circuits. So class, take a break of 5 minutes. After 5 minutes, I'll start with a new topic, series LCR circuit. Exactly after 5 minutes, I'll start with the class. Now LCR circuit means what? LCR circuit means, see here we had individual circuits. We had L separately, we had C separately, we had R separately. Now if a circuit contains inductor, capacitor, resistor, then we call that circuit as an LCR circuit. It means a resistor is connected with resistance R, inductor is connected with inductance L, and capacitor is connected with capacitance C. And obviously we'll have a moving coil galvanometer to control it. So this is equal to E naught sine omega t. This is R, this is L, this is C. So again, repeating the same thing. Current and voltage, voltage of resistance and current, both are in the same phase. For a resistor, if this is the current, voltage of the inductor will lead the current by 90 degrees. For capacitance, if this is the current, then voltage will lag behind by 90 degrees or pi by 2. This is the summary what we have studied. Yes, class. Now one thing. Akifa, tell me one thing. If current in the circuit is I is the current in this circuit and resistance is this. So what will be the potential across this? Yes, Akifa, current is I, resistance is this. Voltage across this part. No idea, Akifa. Resistance is given, current is given. What's the voltage? Aisha? Aisha Rahman, can you try? Current is I, resistance is R. So what will be the voltage? IR. Yes, class. It will be IR. See, voltage across the resistor will be I into capital R. Now, inductance. This is L. So, Atif, what is the resistance in case of a circuit containing only inductor? Yes, Atif.
Omega L.
Omega L or XL. That is the resistance that is offered. So, if resistance is XL, Atif, complete this. If resistance is XL, current is I. So, what will be the voltage across the inductor?
IXL.
I into XL. XL into I or I into XL. Fine. Atif, good. All right. Yes, Fatima. What's the resistance that occurs in case of a circuit of only a capacitor?
1 by omega c.
1 by omega c. Which is what? Which is actually omega XC, we can say. So Fatima, you only complete this if resistance for capacitor is XC, current is I. So what will be the potential across this?
XCI.
XC. Yes, perfect. So these are the voltages. So a quick small revision is also done of the past things that we have studied regarding the individual circuits and also the voltages. Now see here what will happen when you have the full combination of the circuits, no? The phase value and everything, how we have to combine it on a single thing. See, how will the phasor diagram should look like? It's kind of parallelogram law. The way parallelogram law, no, the wherever the net force occurs or net vector resultant occurs there, that becomes the direction. Similarly, here also same thing occurs. So let's say resistance of is VR. This is VR. Potential, not resistance. Sorry. So for resistor is this potential for the inductor. Potential for the inductor, EMF leads. So potential will be VL like this. And for capacitor, it will lag behind. This is how we draw the phasor diagram for the series LCR circuit. Is the phasor diagram for series LCR circuit. Now C class, what happens is that in this two things can occur. One thing is that either VL can be greater than VC, or second thing that is possible is VC greater than VL. Fine. See, when VL is greater than VC, it means when you subtract these two, which should be written first, VL minus VC or VC minus VL? Definitely, if VL is greater than VC, we will write the net resultant of both of these as VL minus VC. So when you subtract, the net resultant will point towards this direction. This will be equal to VL minus VC. If this is the case, then you will write VC minus VL. Here the resultant is towards this. In this case, what happens? You get the graph like this. This becomes VR and this becomes VL minus VC. Here you have VR and here you have the resultant VC minus VL. Like this only. You have to write it for your answer. Now for the solving part, you require an impedance triangle. Impedance triangle is required. So impedance triangle is basically a right angle triangle. This is what? This is Z. This is R. Z is the impedance that I'll tell you what is impedance. R is resistance you are aware of. Now this side, now the perpendicular side of this, let's say this is some angle phi, the perpendicular side of this impedance triangle. This can either be XL minus XC or it can be XC minus XL. That depends on whatever is greater to it. It can happen that XC is greater than XL, so you will write it as XC minus XL. If XL is greater than XC, then you write it as XC minus XL. Now from here, what do we do? Potential, let's say the resultant, potential E naught. E naught is this. This is VL minus VC, this side. And this is VR. Fine. These are what? These are the potentials. Let me write it in the brackets. These are the potentials. This is the potential for this side. So E naught square, if you apply Pythagoras theorem, E naught square will be equal to what? VR square plus VL minus VC square, right? And E naught can be written as, E naught can directly be written as I naught, or even leave E naught right now. E naught using Ohm's law, leave it. VRs you can write. VR just now you have told me. If current is I naught, resistance is R, this will be it. Plus VL will be equal to XL into I naught minus XC into I naught whole square. This much. From here, E naught square, we can take at least I naught square common out from here. If I naught square comes out common, what is left? R square plus XL minus XC is left. This is actually the case 1. This is case 1. This is which case? When your VL is greater than VC. That's why we are considering this. Fine. Now class, if we just remove the square, if we just put the under root on everything, we get E naught as I naught under root R square plus XL minus XC. From here, if I bring this term in the denominator, I naught will be equal to what? E naught divided by R square plus XL minus XC. C class, from here, are you able to notice the fact that this is the resistance that has occurred? If you compare it with the Ohm's law, I is equal to V by R. V is EMF. Resistance is what? Resistance is this denominator that you're getting. In the earlier numericals, in the earlier questions, we did like this. So we could figure out that this is the resistance. Similarly, you can figure out that this is the resistance. Here, we write and represent it by Z, which is known actually the impedance. Impedance is what? Impedance is actually the effective resistance of the LCR circuit. XL was the effective resistance of the circuit containing only the inductor. R is the resistance of a circuit containing only resistor. XC was the effective resistance of the circuit containing only a capacitor. And Z, impedance is what? This is the effective resistance of LCR circuit. Effective resistance of LCR circuit. This is what is meant by impedance. So one more thing class, case 2 can be what? See, just in case, no. If XC is greater than XL, then Z will be equal to R square plus XC, square is here. XC minus XL whole square. If anywhere you're not able to understand between C and L, just ask me, because while writing fast, XC and XL can get interchanged. Square I have missed. See, a square will be here as well. Square is there, no? So this will be the value of impedance. So you just have to figure it out, which value is greater. Fine class, you have to figure it out. And in case if XC and XL are not given directly, omega is given. In terms of omega, if it is written, then in terms of omega, if it is asked, you can write it 1 by omega L minus 1 by omega C whole square, whatever is mentioned. And in this impedance triangle also, let me just compare both the cases with you, if at least you get a clear idea of the cases. Here I have Z, R, XL minus XC. Here I have Z, R, XC minus XL. A short conclusion so that you remember what we have studied. This is the case when XL is greater than XC, or you can say VL is greater than VC. This is the case when you can say XC is greater than XL or VC is greater than VL. Fine. This was phi that we had considered. So from here you can find out tan phi also. Tan phi will be equal to XL minus XC divided by R. And here tan phi will be equal to XC minus XL divided by R. If you have to find cos phi will be equal to Z divided, R by Z. R divided by Z, cos phi is equal to R divided by Z. On both the sides, you have the value same. Fine, it's just that depending on whichever has the greater magnitude, it will keep on shifting. Is this clear? LCR series circuit. Clear to all of you? Any doubts? We have just combined inductor, capacitor, resistor together. Is this clear? Huzefa, Kulsum, Sara, Sneha? Hamza, what about you? Aisha, got it? Okay, Sneha. Atif, clear to you?
Yes, teacher.
All right. So note it down. Wherever you get stuck, ask me, because this is one of the major core topics of your AC circuit. This is the most important topic. We'll do numerical so that this portion will get much clearer. See, in this question, you have to determine the impedance of LCR circuit. If the reactance of C and reactance of L means capacitive reactance XC is 250 ohms, XL is 220 ohms. So XC is equal to 250 ohms, XL is equal to 220 ohms. And R is given what? R is given as 40 ohms. So clearly class, this is the case when XC is greater than XL. So impedance formula will become what? Under root R square plus XC minus XL square. In order to avoid that negative sign, we put this before whatever the term is greater. So Z will be equal to what? Under root R square means 40 whole square plus XC minus XL, that becomes 250 minus 220, 30 square. So this answer will be directly 50 hertz because obviously these three form Pythagorean triplets. So this will be the answer. Quickly note this question and the solution. One last question I'll give you. Now see here you have to find out the readings of ammeter and voltmeter. See when I write Z, Z will be equal to under root R square plus XL minus XC or XC minus XL whole square. But if you notice over here, XL is equal to 4 ohm and XC, this is also equal to 4 ohm. So here what will be Z equal to? Under root R square, that is R. So Z will be directly equal to 45 ohms only. So reading of the ammeter, that will be equal to IRMS, which will be equal to ERMS divided by Z. ERMS is given as 90, 45 is Z, this becomes 2 ampere. This is how you calculate the IRMS. And for the voltmeter, see voltmeter will be what? Net resistance into the current. That is how we write current means IRMS. See, these are 0. Voltmeter will give you 0 reading. Now, why did I give you this question? There was a significance of having this question. This condition, no, where your XL and XC both are equal. For example, in this question we had it. This is known as the resonance condition. The resonance condition of a series LCR. Resonance condition of a series LCR circuit. Resonance condition means what? Resonance means this is the condition, no, when the current is maximum. So see in the formula E naught is equal to I naught is equal to E naught divided by R square plus XL or XC minus XL, whatever whole square. When this term is very less, then only we'll have the current greater. So see, resonance means what? It's the condition. In the exam, you can get a question. What do you mean by the resonance condition of a series LCR circuit? Calculate the resonant frequency. So series resonant, this series LCR circuit is said to be in resonance when the current through it has the maximum value. And through it has the maximum value. This is known as the resonance condition. So in this, one thing will happen for sure. One thing that will happen is XL will be equal to XC. It means omega L will be equal to 1 by omega C. So omega square can be written as 1 by LC and omega is equal to 1 by under root LC. From here, you can even write down the linear frequency. See, if omega is this, frequency is what? Frequency is omega divided by 2 pi. So frequency becomes equal to omega is 1 by under root LC. This is 2 pi. So this is the frequency. And this is what type of frequency? This is known as the natural or the resonant frequency. This frequency, no, this is known as the natural or the resonant frequency. So this is what frequency? This is the frequency where I naught attains a peak value. I naught attains a peak value, means maximum value of current that you have. Now here one more important thing. Firstly, you have to remember XL is equal to XC. See, if XL is equal to XC, what will happen in the formula R square plus XC minus XL whole square? XE will be equal to XL. So it means in this R square plus XL minus XL you can write. These will cancel. You will get under root R square, which will be equal to R. So Z becomes equal to R. Z becomes equal to R. Then only you'll have a lesser value. Fine. So the frequency at which the current amplitude I naught attains a peak value is called the natural or resonant frequency of the LCR circuit. And this resonance condition is what? It's whenever a series LCR circuit is in resonance, current through it has its maximum value. For the calculations you have to remember this. resonance. Whenever resonance term comes, remember XL is equal to XC. And this small derivation also comes to prove the frequency of the resonant frequency. Fine, so this I was relating to you with the help of this question. Note down this. And text me done when you have written. What about others? Shara, Akif, apart from these three? Others have also done? Fine, class. And all those who have written, you can leave. Major chunk of AC was completed today, but do practice whatever assignments you are given. Do practice this and come. So next, I think it was Thursday today, no? So on Tuesday, we'll try to wrap up this lesson. Tuesday or Thursday. Next week, we'll complete up this lesson. But do revise and come. Because soon you'll be going to have a test on this lesson. Completely. All right, class. Take care. Okay. Thank you so much. Goodbye.
Thank you.